In this section, we discuss conditional probability and independent events. Let's start with the following introductory example. Imagine that you have 4 cities, A, B, C, and D, and we want to find the probability of city A hosting the game. The probability of city A hosting the game is 1/4. And if the city D decided not to participate, or it decides to pull out of the contention for some reason, then the probability of A will increase, will change to 1/3. And that means the probability of the event A is affected by the occurrence of the other events. So we have what can be called dependence of events. And later in this lecture, we'll discuss independence of events. Now let's start with the first part of the lecture. It's conditional probability. Now for conditional probability, imagine that you have 2 events where we want to find probability of occurrence of one of them if we know that the other one has already occurred. So here we have conditional probability. So the conditional probability that event B will occur given, this is the condition, given that the event A has already occurred, is given by this formula. Probability of B given, this is red, given the vertical line, red line segment is red, given probability of B given A is equal to probability of the intersection over the probability of A. So here we divide by the probability of the event being occurred, which is probability of A. So now we have how to read this. We read this as conditional probability of B given A. And that means A has already occurred, and we want to find the probability of B. Now here we can think about this as if we draw a Venn diagram. This is A, this is B, this is the intersection. The probability of the intersection over the probability of the whole A. That's that portion divided by the intersection, the probability of the intersection over the probability of the whole A, event A, is the probability that we want to compute, or the conditional probability. Now let's take some examples. Now the first example here, 2 cards are drawn without replacement from a well-shuffled deck of 52 cards. Now the first question is that what is the probability that the first card drawn is an ace? So we are drawing 2 cards and we want to know what is the probability that the first card drawn is an ace. So if we want to write this as events, we can find this. We can write, for example, the second one, or the event, the main event is this. The first card drawn is an ace. This is the event, say E. Now what is the probability of E? Now here in this part we don't have any condition, so we just asked to find the probability that the first card is an ace. So probability that the first card is an ace is number of aces over number of elements of, or outcomes of, the sample space. Number of aces is 4 and number of outcomes of the sample space is 52, and that's 1/13. Now for the second part, what is the probability that the second card is an ace given, that's a condition, given that the first card was not an ace. So let's call this after the condition or conditional event A, and the other condition is B. The condition that we want to compute is B. So we want to find probability of B given A. So if we apply the formula, the above formula, this is probability of B and A, I mean P intersect A, over probability of A. Now here, if we want to find it directly, you can think of this as the first one was already selected, and the second one is the second, so the sample space will be reduced by 1, so it becomes 51, and the first was not an ace. That means we still have 4 aces to choose from them. So we have 4 out of 51 because the first card was already selected or chosen, so we have 4 out of 51. Or we can apply this formula. We want to find this probability. So if we graph some like tree diagram and say that this is ace, this is not ace, and for the first, I mean for the first card. For the second card we may get ace or anything not anything other, not ace, and same thing here, ace or anything else. So the second one is an ace, so the second one is an ace, and the first one is not an ace. So the second one is an ace and the first one is not an ace. So here probability that the first one is not an ace is 48. We have 48 cards that are not aces over 52, and then the second card can be ace. We have 4 aces, but out of 51 cards because we already choose one of them, so that is 48 over 50. Now we multiply this branch, the probability on this branch, 48 over 52 times 4 over 51, all divided by probability of A. Probability of an ace is 4 over 50, or sorry, probability of A is not an ace. A is not an ace, so that's 48 over 52. And then we can cancel these to get 4 over 51. So as I mentioned, you may do it this way, or you just say that the second card, we want to find the probability that the second card drawn is an ace, and that means we have to find the number of aces in the second stage of the experiment if the first one was not an ace. So we still have 4 out of 51 because the first card has already chosen. Now for part C, what is the probability that the second card is an ace? So let's call this event B. Given that, this is the condition, the first card was an ace as well, so we want to find the probability of B given A. The second is an ace and the first one was an ace, so that's probability of the intersection over the probability of A. So probability of the second one is an ace and the first one is an ace, so we have 44 over 52. That's the first card to be chosen. So we have 4 aces and it's the first one is an ace, so we have 4 aces out of 52 cards. And for the second one we have 3 aces out of 51 because we reduced 1, subtract 1 from the sample space because we already chosen one, selected one card in the first stage, all divided by probability of A, probability that the first drawn card was an ace, that's 4/52, and then we cancel these to get 3/51. Or you can do it simply by just thinking of this as the second card is an ace and the first one was an ace. So for the second card, probability for the second card to be an ace, if the first one is an ace, is we only have 3 aces for the second card because the first one was already selected, out of 51 because we already selected one, so the sample space was reduced by 1. Now let's do another problem. Here for example 2, we have a pair of dice is rolled. What is the probability that the sum of the numbers falling uppermost is 7? Okay, so the sum is 7, 1, 6, 6, 1, 2, 5, 5, 2, 3, 4, 4, 3. All these are the outcomes, the possible outcomes. So 1, 2, 3, 4, 5, 6 outcomes. So they give sum equal to 7. Now if it's known that, that means we have some condition. Known that, that means given that one of the numbers is 5. So this is condition A, or the event A, and this is the event B. So probability of B given A is probability of A intersect B over probability of A. Now the probability that the sum is 7 and the number of this means this intersection means the sum is 7, the sum of the falling uppermost is 7, and the 5 is one of these numbers. So as we can see here, we have 5 here and we have 5 here. So those are 2 out of how many outputs or outcomes of this experiment. We are rolling 2 die. That means the first die is 6, has 6 outcomes, the second one 6. 6 times 6 is 36 using the counting principle. So 2 over 36 over probability of A, probability that one of the numbers is 5 in general. How many cases we have? 5. We have 11 cases. I mean 5 with 1, 5 with 2, 5 with 3, 5 4, 5 with 5 with 6, 7, 6, sorry, up to 6, and then we take the other order, 1 with 5, 2 with 5, 3 with 5, and as you can see, 5 is already taken in the first, when we first counted these, so we get 11 outcomes out of 36, the number of outcomes of the sample space, and then we can cancel 36 to get 2 over 11. Let's do another example. There are 300 seniors at a high school, of whom 140 are males. It's known that 80% of the males and 60% of the females have their driver's license. If a student is selected at random from the senior class, what is the probability that the student is a male? The student is a male and has a driver license. So a male, let's call this event M, and driver has driver license, let's call this D, event D. So what we want to find, in the word and means intersection. So want to compute probability of M and D. Now to find this, we can use the conditional probability formula or rule to find this intersection, because we know that we know that probability of people who have driver's license, given that they are males, is probability of the intersection D and M over probability of males. And here we are, why we divided by probability of males, because the portion of the population that we are interested in is the population of males, or subpopulation of males here, and that's why we condition over M. So that's why we divide by M, and we consider the condition is the event M. Now we want to find this probability, so we just solve this. We can find that probability of D and M is equal to this times this, probability of M times probability of D given M. Okay, now what is probability of M? Now probability of M, probability of having a male, when we select a student, how many males are there? We have 140 out of 300 seniors. So this is the probability of getting a male times probability of getting someone who has driving license, giving that person is a male. This is equal to 0.8. I mean 8%. 80%, those are the people who have a driving license and they are males, or given that they are males. So the probability here is 0.8, or 80 over 100, or 0.8. That means this probability is, using the calculator, we find that the probability is 0.373. Can be approximated as this. Okay, so we can use the conditional probability rule to find the intersection, probability of the intersection. Now let's do another problem, or part B. A female, we want to find that the probability that the selected student is a female. Let's call this event F, and means intersection, does not have a driving license. That means driving license complement. I mean the population or the people who have driving license, complement of that is the D complement. Okay, so here in this case we still want to find probability of F and not D, complement of D. Now how to do that? We can apply, since we are interested in population of females, we have probability of D complement intersect F, and that's probability of D complement given F. So we know that probability of people who don't have driving license, given that they are females, is 40%, because 60% of females have driving license. So that means the portion of the females who doesn't have driving license is just 40%, or we can write it as 0.4 equals. Now we want to find this intersection over probability of female. Probability of female, how many females are there? We have 140 males out of 300 seniors. That means we have 160 females. So 160 females out of 300 seniors. That's the probability of selecting student who is female. And then we solve for probability of D complement intersect F. So probability of D complement intersect F is 0.4 times 160 over 300. We can cancel 0 and simplify more, so we get 0.4 times 8 over 15. And using calculator, we get something like 0.213. Now let's do another problem. 2 cards are drawn without replacement, and from a well shuffled deck of 52 cards, what is the probability that the first card drawn is an ace and the second is a face card? Now, how many face cards are there? As you know, we have Jack, Queen, and King. We have 3 of each type, spades, hearts, etc. So we have 12 faces. I mean cards with face on it. So we want to find, now here we have word and, so we need first to determine the events. The first event is the first card drawn is an ace, so let's call this A, and the second card is a face, let's call this F. Now we want to find probability of getting an ace on the first card and a face on the second one. So that means we need to find this probability of the intersection, but we know that we can apply the conditional probability to find this. Now here we have probability of the intersection, a face and ace, or ace and face, ace on the first card and ace on the second one, over probability of ace, because we want to find the probability of the, now we're talking about the probability that the first card is an ace and the second card is a face. So here we are conditioning on the first card, and here we have the face. So probability of getting a face on the second card, given that the first card, so here the condition, the first card is conditioned, so we want to find the probability that the second card is a face, given that the first one is an ace. So we need to divide by probability of A. So once we write the formula or the rule, then it becomes easier to find the probabilities. Now, probability of the intersection, ace on the first one and face on the second one, is the product of those two probabilities, probability of A times probability of face on the second, given that we got an ace on the first card. Now, what is probability of getting an ace? We have 4 aces out of 52 cards, times what is the probability of getting a face on the second card, given that the first one was we got an ace on the first card. Ace is not a face, so that means we still have 12 faces out of how much? How many? This is out of 51, because we already chose a card in the first part of the experiment. So we have 51, 12 over 51, because the first card was already chosen, and that means we subtract 1 from the sample space, or number of outcomes of the sample space, and using the calculator we get 0.018. Now that was conditional probability. Now let's talk about the other part, or the some important part of events, and that's called independent events. So here the definition says 2 events A and B are independent if the occurrence of one does not affect the probability of occurrence of the other one. Now, for example, if we are tossing a coin where H is getting head and T is getting tail for tossing a coin, those 2 events, H and T, are independent, because the occurrence of one of them does not affect the probability of the occurrence of the other one. The probability of getting head is 1/2, the probability of getting tail is 1/2. So they are independent. But if we have the first card is, if we are in the previous example, we are choosing a card, select two cards, one of them in the first one, for example, we get a face, and in the second one another face. That means it's dependent because number of face cards will be reduced and the probability will be less. So that means the probability is affected by the probability of or the occurrence of the other event. So that means that is not independent. But for tossing a coin, it's independent. Now, if we know that the two events are independent, then we know that the condition on, the conditional probability, probability of A given B is the same as probability of A, because B will not affect the probability of A. Same thing, probability of B given A is the same as probability of B, because the other event A will not affect the probability of the occurrence of the event B. Thus, we have that probability of A intersect B is the probability of B times probability of A given B, because this is from the conditional probability. A given B is probability of A and B divided by probability of B. Then if we multiply these two, we get the intersection. So the intersection is probability of A times probability of A given B. But we know that probability of A given B is just probability of A. The condition will not affect the probability of A. So we get probability of A times probability of B, and that's very nice result because we don't need to compute other things. If we want to find the probability of the intersection of two independent events, all what we need to do is to find probability of the first event and probability of the second event and multiply them together to get that probability. Now we have two concepts, the mutual exclusive events A and B. We know that from the first lecture of this chapter that two events are mutually exclusive if they are disjoint. This is event A, this is event B. Those are disjoint. That means the intersection is phi, and that means the probability is 0 because probability of phi of nothing is 0. So if we want to check if two events are mutually exclusive, we need to apply the probability of the intersection. If the answer is 0, that means they are mutually exclusive. And here we mean by mutually exclusive that the two events cannot occur at the same time. For example, a single coin toss, we either get head or tail. We can't get head and tail at the same time, so they are mutually exclusive. The another concept is the independence. A and B are independent, as we described before, if the occurrence of one of the events does not affect the probability of the occurrence of the other event. And in this case, as we find here, probability of the intersection is probability of the A times probability of the event B. We just multiply the probabilities of the events. For example, tossing a coin and rolling a die and landing on head and rolling a 4 on the die, those are independent events. Now let's take an example. We want to determine if the events E and F are mutually exclusive and or independent. So we are given some probabilities here. We want to check first if they are mutually exclusive. As we described, they are mutually exclusive if the intersection gives 0. So let's check this first. Probability of E intersect F is given to be 0.2 is not equal to 0. They are not mutually exclusive. Now let's check for independence. They are independent if probability of A intersects F or E intersect F is the probability of E times probability of F. So let's try this. Probability of E intersect F is 0.2. Is it equal to probability of E times probability of F? Probability of E is 0.5. Probability of f is 0.4, and this is 0.2 as well. That means the left hand side equals right hand side. That means that they are independent. They are independent but not mutually exclusive. Now, second part, we want to check with these conditions, events E and F. So let's start with the condition with determining whether they are mutually exclusive or not. Probability of E and intersect F is given to be 0.3, and that's not equal to 0, so those are not mutually exclusive. Now let's check the second thing, the independence. The probability of E intersect F, is this equal to probability of E times probability of F? Let's see. Probability of the intersection is 0.3 given. Now probability of E is 0.5 and probability of F is 0.7, and when we multiply them we get 0.35, and that means they are not equal, so not independent. The two events are not independent. Now part C, we want to check if the events E and F are mutually exclusive. Probability of E and F, or intersect F, is equal to 0. That means yes, they are mutually, E and F are mutually exclusive. Now let's check for independence. Probability of E intersect F, is it equal to probability of E times probability of F? The left hand side is 0. The right hand side we have probability of E is 0.1, probability of F is 0.3. 0.1 times 0.3 is 0.03, and those are not equal. That means they are not independent.